Hello, Algebra 2 local students. I hope that you feel like you successfully got through some arithmetic sequences. And now we're going to move on and talk about a new type of sequence known as a geometric sequence. And that will be the focus for the rest of this week. And we will pick it up again after spring break. So some of the stuff that I do today, if I go too fast at all, you guys know what to do. Just pause and, kind of catch up to where you need to be. When I'm not teaching in front of a group of students, sometimes I might move a little bit faster than I normally would. But we have a definition already filled in for you at the top of the notes, which says that a geometric sequence is where each term is found by multiplying by a constant. That constant we're going to define as the value of r, because r is known as the common ratio, which is in the next definition. The common ratio is the number that you are multiplying by in a geometric sequence. So I called it the multiplier. Okay. So as compared to arithmetic, where we were adding a constant amount each time, now we're going to look at a sequence, a pattern of terms where we multiply by a constant amount. So in this practice, we're going to look at some sequences and determine yes or no to see if it would be a geometric sequence. And if so, then we'll state what the common ratio r would be. So actually, if you want to pause quick for a second on your video, take a look at these 6 examples. See if you can determine yes or no for the following. I'm going to pick up right away here and say that in number 1, this is a big old yes, it's a geometric sequence. Now, if it wasn't obvious, the r value is 4. So what you can do is you can pick any 2 terms that you'd like, the second term and the first term, divide those, you get 4. Now, when I say any terms you like, I guess I should clarify that and say they have to be consecutive, meaning one term comes after the other. And I'm feeling this is a little bit tough for you guys to see. Do I have a light here? I don't know if that, that actually did help. Nice. Okay, so if I pick any consecutive terms and I divide by the term that came before it, I'm always getting that same r value of 4. So that's kind of a quick way to double check whether it's geometric or not. If you look at the next case, number 2, 5, 10, 15, it looks like a nice pattern to me, but this one's a no. It's actually arithmetic with a common difference of 5. So we're not multiplying by a constant amount, but it looked familiar probably because it's an arithmetic sequence. All right, in number 4, 1, 4, oops, sorry, I should probably have gone to 3, but that's okay. 1, 4, 9, 16, 25. Wouldn't the next one be like 36, 4? Those are nice numbers, right? Those are perfect squares. Well, even though they're perfect squares, you're definitely not multiplying by the same number to get from one to the next. So this one's also a no. When I look at number 3, coming back across the way here, 80, 40, 20, 10, 5, it's maybe not obvious right away, but this one's a yes. Even though the terms are decreasing, think about what could I multiply by to get from one term to the next. And I think a lot of us would say, oh, Mr. Earl, you're dividing by 2. Well, dividing by 2 is the same thing as multiplying by 1/2. So the r value is 1/2. You can check that by doing 40 divided by 80, which gives you 0.5. If you want to math frac it to convince yourself, of course, that would be 1/2 in this case. 7, 7, 7, 7, 7, 7, 7. Lucky sevens is geometric with an r value of 1. You multiply by 1 constantly, you're going to get 7, 7, 7, 7, 7. It's also an arithmetic sequence with a common difference of 0. So that's a unique list of numbers because it can be classified as both, being arithmetic and geometric at the same time. Let's see, the last one, 16, 24, 36, 54, 81. I mean, I don't know exactly what I would multiply by to get from 16 to 24, and if that's the same thing to get from 24 to 36. So when in doubt, check it on the calc. 24 divided by 16 is 1.5. 36 divided by 24, also 1.5. Let's just check one more. 54 over 36, 1.5 again. So this is a yes with a ratio of 1.5, or if you love fractions, you can say it's 3/2 there. All right, now that we kind of have a little bit of a better understanding about geometric sequences, in this section right here, we're going to figure out what the value of r is and then fill in the missing blanks. In number 1, to get from 4 to 12 and 12 to 36, we're multiplying by an r value of 3. So if I multiply by 3 again, 36 times 3 is 108. Times 3 again would be 324. So we can fill in those missing blanks. Okay, 11 and 121. I'm pretty sure the r value here is 11. You can double check it, right? Because you would do 121 divided by 11. Yep. So 121, this is kind of a fun sequence. Look at what happens to these numbers. We get 1, 3, 3, 1, times 11 again, you get 14641. Sounds like somebody's zip code, but these numbers are all, they're kind of nice little palindromes at the same front, forwards and backwards. So that's weird, but fun. This one, I actually want to go backwards, right? So if I'm going forwards, the R value I'll tell you in this one is 2. So if I have to work backwards from 72, then you have to divide by 2. 72 divided by 2 is 36. Divide by 2 again, this would be 18. Okay. So in the next one, 520, the R value from here to here would be a 4. 20 times 4 would be 80. You can even double check that. Is 80 times 4 320? Sure is. Multiply by 4 one more time to get the one after 320, which is 1280. Okay, looking at number 5, first one is 0, and that's the only one we're given. So that's a little bit odd because what would the common ratio here be? Well, it could be pretty much anything. 0 times something is always going to be 0. So this is a sequence of zeros as we go throughout there, but the R value could be, pick your favorite number, it doesn't really matter. And in this last case, 16, 40, 100, maybe not a super obvious R value. If you divide out the second by the first term, you get that the R value is 2.5. So if you do 100 times 2.5, that should be 250. And if you do that one more time, times 2.5, you get the last term in the list to be 625. So I realize I went through that stuff very quickly, but if something was too fast, again, hit pause, take some time to understand some of the geometric sequence patterns here. Okay, on the next page, we're going to learn how can we develop the pattern for a geometric sequence. And we did something similar for arithmetic sequences last week when we were talking about that pattern. And at the top here, it says, on a popular quiz show in the 1940s, the contestants were asked a series of questions. And each question was worth twice as much as the preceding one, beginning with $1. So this one says, list the amounts that the next 6 questions were worth. So if the first question was $1, the next question would be worth double that, which is $2. And then we would have $4 and $8. And I guess I have 3 more to go, right? 16, 32, and 64. And number 2 says, if n represents the value of a given question in the series, what represents the value of the next question? So pause it for a second. See if you can answer that, and then I'll show you what the answer is here. So the next term in this list can be determined by doing something along the lines of, if I'm consistently multiplying by 2 to get from one term to the next, it definitely has a connection of 2 raised to some power. In fact, it actually really is 2 to the n minus 1. And you can double check that for me real quick by saying, hey, what's 2 to the 7th? Or if you plug in n equals 7 for the 7th question, 2 to the 7 minus 1 would be 2 to the 6th, which should give you the $64 that question 7 was worth. So you can double check that there, but when you repeatedly multiply by something, in this case 2, that becomes the base of an exponent. So we're going to see how that pattern really plays a role into developing general geometric sequence patterns. In this next section, the terms are 2, 6, 18, 54, and 162. We really quickly have to look at that and know that the ratio is 3. 2 times 3 is 6, 6 times 3 is 18. The numbers get a little bit larger from there, but hopefully you'll trust me that the ratio is 3. So the first term, A1, is 2. So you're going to fill in there for the first term. So to get to the second term is 6. I want you to think of that as being 2 times 3. And 2 times 3 is the same idea as taking A1 and multiplying by R. Okay, building on to the third term. The third term is, in this case, 18. How do I get that? I take what I had in the last step, 2 times 3, and we multiply by 3 again. So this is going to be A1 times R, and I'm hoping you remember, hey, R times R would be R squared. Third term, we're taking A1 and multiplying by R squared. Build it out one more term, 54 would be what I had in the last step, times one more of those ratios of 3, which is A1 times R r, and r, which could be written as a1r cubed. So to get to the fourth term of the sequence, we're taking a1 and we're multiplying by r 3 times. So the connection here is that if you want to find any term of the sequence, and this is a notation you should be familiar with from last week, any number term in the sequence, an, would be equal to the first term a1 times that ratio r n minus 1 times. Okay, to get to the fourth term, it was r to the 4 minus 1, which is 3. To get to the 100th term, you'd multiply by r 99 times to make that happen. So based on that, could we quickly find the 10th term of the sequence? Sure, a10 would be a1 times r to the 9th. So I plug in a 10 up for n right there. 10 minus 1 would be 9. a1 is 2. The ratio is 3. It's going to be a pretty large number here, right? 2 times 3 to the 9th, or maybe we didn't know that, 39,366. So the power of exponential growth really makes the terms in sequences like this grow much, much faster. And number 2, not sure if you guys would have even caught this, but it should say given the geometric sequence, not arithmetic there. So the terms are 3, -6, 12, -24, 48. What's interesting about geometric sequences is you might see those signs start to alternate, positive, negative, positive, negative. And that's okay, because if the ratio is negative, in this case the ratio is -2, you'll see that positive times negative is negative. Negative times -2 is positive, and so on. So the signs will switch as you go throughout. How am I going to get the 8th term? The 8th term in an geometric sequence is a1 times r to the 7th, using the pattern that we just developed. a1 is 3. The ratio is -2. It's going to get raised to the 7th power. Okay, 3 times -2 to the 7th is -384. I'm guessing you guys can probably develop the pattern for the 12th term. It's really not that different than finding the 8th term. So check out the answer on the website later to see if you got the correct answer for that question. Moving on to the next set of examples, we have in number 3, find the 21st term of this geometric sequence. I might be able to convince you that you might not need a formula for this one. The formula for the 21st term would be a1 times r to the 20th. So a1 is 2. The r value in this case is -1. And trust me that if you plug those numbers in here, you're going to get the correct answer. However, if you look at the terms, which are just alternating back and forth between 2 and -2, since the 21st term is an odd number term in the list, notice how the odd number terms are positive. So I'm pretty confident that a21 is going to be a positive 2 as opposed to a -2. Check it out using the formula, see if you get the same answer. In number 4, find the 10th term of the sequence. So we have this list here. If they're decreasing, just remember that the r value becomes a fraction. 16 times a half would be 8. Half of 8 is 4, right? So a10 would be a1 r to the 9th. a1 is 16. The ratio is 1/2. So 16 times 1/2 to the 9th. Don't be surprised if you sometimes get fractions or decimals. I got 0.03125. It's acceptable as long as you write that whole decimal out. Maybe you'd like the fraction better, 1/32. So I'll write down both just so you guys have it there, but it's 1/32, or if you like the decimal, 0.03125. Both would be acceptable. Just don't round that to 0.03. That would not be the same. Okay, I may not do all of these, but taking a look at given a1 and a value of r, could we find the 9th term, or in this case, the 6th or the 11th? Maybe I'll just kind of quickly do a and c here. You guys can go back and check b later. So for part a, a9 would equal a1 times r to the 8th. So that would be 2 times 5 to the 8th power. If I plug that information in, it's going to be a big number here. 2 times 5 to the 8th is 781,250. Okay. And then in part C, a1 is negative. The r value is negative, so just make sure you carefully sub those in. The 11th term would be a1 times r to the 10th. -16 times the r value, -2 to the 10th. Keeping in mind a negative to an even power is going to make that a positive number, but then I'm multiplying it by a negative out front. So the final answer, if I type this in correctly, should be negative. Let's double check it here. Negative 16 times negative 2 to the 10th is negative 16,384. And again, you guys can try part B there on your own if you want to double check that later. The last thing we're going to do kind of quickly here today is talk about how can I use two given terms in a geometric sequence to find the ratio, and we don't know A1 anymore. We did these same exact types of questions with arithmetic sequences, so hopefully it doesn't look too foreign. I'm going to draw some blanks for this first one, just so you kind of get an idea as to what we know about the sequence. If we know the second term is 9, here's the third term, the fourth term, the fifth term is 243. What I'm first going to do is find the common ratio. What am I multiplying by to get from 9 to this many terms later, 243? Well, how many terms later is it is the question. Because I have to use the information that's given. What I want to carefully do is figure out what is this exponent right here. I'll tell you it's not a 4. Because I think we get lulled into this, sense of security of saying, oh, if this is a 5, this number is always 1 less. That's only when this is A1 on this side. So if we were dealing with A2 and A5, how do I determine this exponent? Well, let's just look at the sequence real quick. To get from this term of 9 to this term 243, you're going to have to multiply by the ratio once, twice, and then finally 3 times. So R should really be cubed in order to make this happen. Notice how the 3 up there is just the difference in the terms that we're working with. So when I look back at any of the other examples, isn't 10 the difference of 11 minus 1? Isn't 8 up here the difference of 9 minus 1? So because this is a 1, this exponent here is always just 1 less than the term we were looking for. But if I change that because now we know A2 instead of knowing A1, the difference of the term numbers is your exponent of R. So just try and keep track of that. Plug in what you know. 243 is A5, 9 is A2. And you've seen questions like this with arithmetic sequences. The solve's going to look a little different, though. So to solve for R, first thing I need you to do is divide by 9. To get that R cubed equals 243 divided by 9 is 27. Now, a long, long time ago, I'm guessing it was probably November when we did something like this. If we had an exponent that we wanted to get rid of, what you can do is you can raise both sides to the reciprocal power of that exponent. This is really a 3 over 1. So to get rid of the third power, I want you to raise both sides to the 1/3 power. Careful if you're not doing this on a calculator. If you're doing it on your phone, it might be tough to do 27 to the 1/3 power. But 27 to the 1/3 power should be 3. Okay, so if the R value is 3, can I use that information to find A1? I think the easiest thing to do in this case, guys, is probably just divide 3 to work backwards. Right? If we're at 9 here, going 1 term backwards gets you to 3. So I know that A1, therefore, is 3. Could I quickly confirm that using an equation? Sure. If I know A2, that would equal A1 times R to the first. A2 we know is 9. A1 we don't know. The R value we just determined is 3. And 3 to the first is just still 3, right? So if you divide both sides by 3, you get that A1 equals 3. So quick ways to get it. You don't necessarily have to use this formula, in my opinion, to work backwards there. But if it helps, go for it. All right, and actually, I'll jump down to number 3. I'll do one more of these with you. And then you guys can go back and take a look at number 2 if you need to. So given A2 and A8, so A8 would equal A2 times R to the 6th. Right, so that exponent is just the difference in these two terms that we're working with here. A8 is negative 128. A2 is negative 2. So we're going to, in this case, to solve for R, divide both sides by negative 2 to get that R to the 6th equals negative 128 divided by negative 2 is 64. And just like I did up in this question up here, how did I get rid of the third power? I raised both sides to the 1/3. Well, if I want to get rid of the sixth power, I'm going to raise both sides to the 1/6. And that's going to give me R equals, let's check it out, 64 raised to the 1/6 power should be an answer of 2. And if you're getting kind of wacky answers, definitely check your work, because I'll tell you, we choose the R values to typically be nice-ish looking numbers. So if you get some crazy looking decimal, chances are we made a mistake somewhere. All right, how would I find A1? Again, if you want to just divide by 2 and work backwards, that's fine. Let me show you what would happen if I use the 8th term, because that's another term that we know in the sequence, right? A8 would equal A1 R to the 7th. We know A8 is negative 128. We don't know A1, but we just found that R is 2. And if you type 2 to the 7th on the calculator, you wind up getting that that's actually 128. So divide both sides by that number, and you get that the first term in the sequence would have been negative 1. So I know I probably moved really quickly through some of those examples. Definitely stop along the way if something was going too fast, and reach out to one of your teachers if you have any questions about day 1 of geometric sequences. Thanks for sticking around, guys.